Okay, well, good evening, class. This is Mr. King speaking, and I want to complete section 1.9 in your Math 13-14 class. So I'll call this part 2, and we're going to go over the homework, some of the homework questions in your WebAssign assignment, and make sure you listen and watch lesson part 1 from section 1.9. That should be in your Blackboard course as well. Okay, so I want us to look at problem 19 here. And we already did in the first part problems 21 and 22. And then we had a lengthy discussion about inverses and what they are and how they look with respect compared to each other on a graph, on a coordinate plane, and also the official test to determine if two functions are inverses or not. So we had to check both of their compositions and see if they simplify out to x if we use a general point x for a general domain value x on the first function. Okay. Also, the other thing we did was show how algebraically we can take a function and find its inverse, not only graphically but algebraically. So those are the things we'll be practicing, and so here we go. So this is number 19, and we have two functions given to us: the square root of x plus 3, g of x equals x squared minus 3, and they tell us to verify that they are indeed inverses algebraically and graphically. Well, let's do it first graphically. So they're not telling down here, we're supposed to know and determine which one of these two graphs. So one of these four answers is correct. And for example, notice they tell you here on each one we can choose from as being the correct answer. They say this one is G, this one is F, and so forth. So, yeah. So all of these graphs, well, this one doesn't look symmetrical about the line y equals x, but then sometimes the scaling can mislead us. But let's just go with our knowledge of, let's say we look at this one first, x squared minus 3. When x is greater than 0, so x squared is a parabola, the shift is minus 3, so vertical shift down, but they don't want us to graph the entire graph because they give us this restriction here that x is greater or equal to 0. So, let's see. We know a parabola opens upward when it's positive x squared. We're only going to have half of the parabola, and we know it's shifted down 3 units. So typically, x squared, looks something like this. And now we only want half of that for x greater or equal to 0. So only this part is what they're giving us. But then not only for x greater or equal to 0, but not only that, but now we're going to shift it down 3 units. So we get something like this. As soon as I start to try to make a nice graph of it, I destroy it here. And I'm just making it worse here. That's pretty interesting. Anyway, so I think I need to erase that, okay? So hopefully you understand what we get here. That is about as bad as it can be there. And try one more time. Pretend that is -3, and it still looks pretty bad. But anyway, well, neither one of these has this part that we're looking for G. And this one looks very good. It does go down 3 units to -3. It does look parabolic, half of a parabola, and the blue one is labeled G. So that's a possibility. Let's see about the other two choices. So neither one of these is the half parabola we're looking for, and neither are these two. So it looks like it's going to be this one, but let's go a little further in detail. So if you wished, you could pick another point and just make sure. So for example, the g of x function that we just made a little sketch of, you could graph, one or maybe 2 points. So x greater or equal to 0. At 0, we already said we're going to get -3. That's the vertex, and that's where this parabola starts. Or you could just plug 0 in here and get -3. Let's just pick one more. How about 2? When x is 2, 2 squared is 4, 4 minus 3 is 1, and we get 2, 1. So these are 2 points out of infinitely many points that are on the function g. And and by the way, therefore, if we invert these points, then we better have the inverted points on f of x if they are inverses. So -3 would invert to -3, 0. So let's check, is that that better be on the inverse? If these are actually inverses, which they tell us they are, we're just supposed to show it. And 2, 1 is going to invert to 1, 2. So we had determined already that this is what we thought. Oh no, it had to be this one. So if we now look at this, so let's first of all check the 0, -3 is right here. 2, 1 is somewhere right here. So that looks believable. 2, well, let's see, 1, 2, 3, 4, yeah. So if you go straight across, 2, 1 is on the graph of G. So those 2 points we picked are on this graph. And if we invert it, so -3, 0 is right here, and that is on the other graph, which they called F. And 1, 2 is also looks very reasonable to believe that it's on the graph. And remember, that's just the inverted. This is the point 2, 1. Inverted becomes 1, 2. And 0, -3 inverted becomes -3, 0. And it's also that reflection we talked about in part 1. So this looks very reasonable. So we will pick this one and hope that made sense. Now the other part is, and just to be, just to use this problem as an opportunity, if we pick any one of these, say we pick the g of x and we write y equals, instead of g, what if we write y equals x squared minus 3? And remember, the domain is x had to be greater or equal to 0, then when we find the inverse function, let's say we had to find the inverse, and this is g of x, then g inverse, written as g to the -1, yeah. So first of all, if x is greater or equal to 0, which they gave us, then on the inverse, y is going to have to be greater or equal to 0. Okay, and by the way, this was our choice, and y is greater or equal to 0 here. Okay, so let's see if we can get this equation, x, the square root of x plus 3, by computing the inverse ourselves. So recall from part 1 discussion, to find the inverse of a function, you write down the first function, y equals x squared minus 3 in this case, and then we simply invert the x and the y's wherever they are located. So instead of y, we'll have x. Instead of x squared, we will have y squared minus 3. Right there is the inverse. This is the inverse equation. The only problem is we really want to solve for y to make sure we have taken care of the range restriction here. Because remember, x was greater or equal to 0 on this equation. So when you, on the inverse, then the inverted letter, x then switches to y. So on the inverse equation, instead of saying x has to be greater or equal to y, you're going to have to say y will have to be greater or equal to 0. So if we now solve this equation for this switch to y value, we can move the -3 over by addition. We have y squared still. And to get rid of a square, we square root. And the square root of y squared, the square root of x plus 3. These compose out when you put the squaring function into the root 2 function. They are inverses. So they compose. And really it would be absolute value of y to be precise, but then you would write the next line after that, plus or minus the square root of x plus 3. So, but y, remember, has to be greater or equal to 0. So a square root, a value of a square root is either 0 or positive. So if we multiply that by a negative, it would make a negative, and we can't have that because of this restriction. So it also has to do with whether the inverse will actually be a function. But so then we want to take away this negative part. So this part is going to go away, and therefore we can say the inverse function is just the positive square root of x plus 2. And then that is the inverse equation of the whichever one we started with g. So we could call this g inverse if we wanted to. But it was written over here as f of x, and it's equal to the same thing, notice. So that means we did find it correctly. And so we do know that f and g are inverses of each other. We showed it graphically. We have now done it algebraically. And then, although there is another way to show it algebraically, which I showed you in part 1 of the video, and that is to check the composition of the two functions. So let's do that now. You may remember I had used well, you can, I don't want to repeat all that again. So here's another way to check if functions are inverses of each other. And recall that is to check both order of composition of composing the two functions. So one is if we put g of x into, so remember, we pick like if you could pick a numerical point, we could do that too. That's what we discussed in part 1 video. We had like a 3 and we put it into the squaring function and we got a 9, and then we put that range value 9 into the second equation, which was the square root function, and the square root of 9 goes back to 3, and that gives us an indication that these are inverses of each other. But in general, you show it for any x value, in the domain of G. So instead of picking one specific point, numerical value for x, I mean, we could have picked something, whatever, we could have picked 4 or something, and or 3 or 2 or 1, and we could have done it that way. But the general proof is to put, for any x value, you put that into G. This will be not a number because we're not putting a specific number. It'll be an algebraic expression. And then we put that algebraic expression, which is our range expression. Instead of our range number, it's our range expression. And we put that into this expression. We put it into the other function, and that's the composing part of it. And when we do put it into the other function, if we get back to the initial x value, well, then that's a check, and that would be, we would be halfway done. And then you'd also have to do it the other way around as well. Say you have f of x, you put that into the other function, g, and if you get, okay, sure, thank you. Sorry about that. If we get x again, then that's a yes. And then we can say, therefore, since both composing or compositions get you back to the initial x value, then therefore the two functions are inverses. Seems a little magical when you just use any x value. But I did show you in the part 1 video is if you were to pick a numerical x value, and that also works. But the general proof is to do it for any x value, which really means every x value in the domain of whichever one you pick first, are inverses. So instead of, another way to say that, you can say G is the inverse of F. G is the inverse of F, or F is the inverse of G, or you can just say they are inverses of each other. Okay, or you can just say they're inverses. Okay, so how do we check these two right here? And I'll do this one with my not so pretty mouse pen. And then from then on, we will do it on regular paper and pencil. So this one, let me switch the colors back. So let's do this one. So we're going to take, so let's say we call this the first one, which is like this one. I can draw one. So instead of putting, we could pick a certain number for X and put it into G and get the range value and put that numerical range value into F. And if we get back to that original X value that we started with, then that's a strong indication that they're inverses of each other. Instead of doing it with one specific point, we're going to do it for any X value, which really means then all X values. So this is a proof, a way of showing it for instead of just one specific point, but for all of them that are in the domain of the first function of this function you start with. So what are we going to put right inside of G? Not a numeric number for X, but just any X. And if you put any X into, if you put X value into G, well, instead of X right here, you just put the X and you still get the same thing. So instead of putting like a G of 4, and then you'd put a 4 right here, 4 squared minus 3, and then compute, we're going to leave it as a general of any X. And so then we don't get to put the 4 right here or whatever, because we're not picking a specific value for X. We're saying for any X. So therefore, that's why we get right here the expression, the algebraic expression for, it's the algebraic range expression for G of X. So instead of getting a numerical range value, again, if we would put a 4 in, if I just pick 4 for X, if you put 4 into this function G right here, 4 squared is 16 minus 3. Well, since I keep saying it, let's just try. So what if we picked at X equals 4? So one more time, on part 1 we did this, but let's try it one more time with a specific numerical value. So at X equals 4, G of 4 we would plug that in to G, and that is the 4 squared minus 3. That's supposed to be a 4. And 4 squared is 16. 16 minus 3 is 13. And that's our range value. Now take this range value and put it into the other function, f, and we would have 13 going into the function f, and we better, if we get 4 back, because that's what we started with, this means again 4, 13 is on the graph of G. So now we're going to find out if you put 13 into F, which is, what do we get? Well, if we get 4 right here, then that's that's an indication, at least with this X value, that when you put this X value into G and you get the range value, and then put the range value into the other function, if you get back to 4, well, then that's an example of these functions being inverses of each other. So let's see. If you put 13 now into F, so that would be right here. F is the square root function, x plus 3, but instead of x plus 3, we would put this 13 plus 3, and 13 plus 3 is 16. That's a 13. And the square root of 16 is 4. So we did get what we were hoping for. So again, what that means, everyone, is if we draw a table for G, this is for G of X. And if we draw a table for F of X, then what have we just shown? That if you put 4 into G, you get 13. What that means is the point 4, comma 13 is a point on the G function. And now we have shown that 4, 13, 4 is on function f. And not only do we show that it's on the function f, but more importantly, we show that, again, if you pick an x value, put it into one of the functions, in this case g, you get the range value 13. Now put that range value 13 back into the other equation, f, compute, and if you get 4, well, then you just showed that 4 and 13 is the inverse partner to 13, 4 from these two equations. So yeah. Okay, so instead of doing it with x equals 4, we're going to do it in general. And so we have this right here. Oh, one more thing. One more thing. So what did we just show over here? That we just showed half of it. That if you put G of 4 into function f, you get back to 4. Yeah, so that's what we just showed right here. Put 4 into G, you get the range value 13. That's this part is 13. Put 13 into F, that's what we did right here, and we get 4. Yeah, and now we're going to do it for any x value. So instead of saying at x equals 4, we're saying at any x. So what we're doing right here is this one. At any x value, so instead of saying G of 4, put that into F and get back to 4, we're saying at any x value, not just 4, put x into G, whatever that becomes, that range value, put it into F, and let's see if we get back to the original x value. Now, G of x is like the G of 4 here, but since we're not putting a specific number in for x, we're going to get an algebraic expression instead of the 13. So that's why after writing this as the first thing we're going to check, instead of G of x, instead of putting the 4 in and getting 13 and writing a 13 here, we just say put an x into g. Well, if you put an x into the g function, you get the same thing as this, x squared minus 3, because this is just for any x. For any numerical x value that's in the domain, you put it in and you get range expression x squared minus 3. Now put this into the other equation, and that's like putting now the 13 into f, 13 into f. And so now we're about to do that. So we're going to put x squared minus 3 into function f, and we hope to get x back. Not the 4 back like we did here, but just the general any x value back. So that will mean it works for any x value in the domain. Okay, so how do we do this? Go put x squared minus 3 into the f function wherever there's the x. So instead of putting the 13 right here, and so we're going to write equals square root plus 3. And instead of putting the 13 into right here, yeah, we're going to put, well, this algebraic expression. So we get x squared minus 3. And now we simplify. Well, there's an invisible multiplication of 1 here. 1 times x squared minus 3 won't change anything. So we get square root of x squared minus 3 still, plus 3. And now I'll clean this up. The negative 3 plus 3 add up to 0. So we're left with x squared. And then the square root of x squared is x. But really it's plus or minus x. But remember, x has to be greater or equal to 0, so we don't have to write the negative x. So we can just write x. And now we did get, that's a check. So yes, it did work. So just like when we put 4 in to g and then put that range value into f, we did get back to 4. Now that happened for any x value. And now that's just checking this one. Now we have to do the second one. And then it'll start to go faster. Okay, so let me erase some of this. Okay. So now we're going to do this one right here. So we're going to take, well, I have it written right here, so I'm not going to write it again. So we're going to take f of x and put it into g. So, but we're not going to pick an x value again. It's for any x value. For any x value. For any x value. It would really be for any x value that is in the domain of f, which is starting right here at -3 and onward. So if we picked any x value from -3 and on, put that number into f, get its range value, and then put that range value into g, then we would want to get back to that same x value. So I could show you with a numerical value, but it's already taken a while here. So let's just do this. So instead of putting a specific numerical value into f, I mean, just pretend, say you put 0 in, then you would put 0 here, and you would get 0 plus 3. Now let's say you put a 1 in. 1 plus 3 is 4. The square root of 4 is 2. So I just said x equals 1. So we can check it real quick. So if we put a 1 right here into f, that's a 1. So 1 plus 3 is 4. The square root of 4 is 2. So this would become range value 2. Now plug 2 into function g. And if you plug 2 into this other function g, 2 squared is 4. And 4 minus 3 is 1. So we do get back to this initial value 1 without me writing it all out. Okay, so what are we going to put here in general for any x value? Well, for any x value into f, so instead of putting a 1 right here or a 0 or a 2, we're going to put any x. So that just means you leave the letter x. So it represents any x, any numerical value x. And so we will get the square root of x plus 3. I'll put that into, so that's when we put 1 into here. 1 plus 3 was 4. Square root of 4 was 2. And then we put 2 into the g function. And then 2 squared was 4. 4 minus 3 was 1, and we did get back to what we started with. So now instead, we're going to put the general expression for any x into f. You don't get a numerical answer like 2. You get just this algebraic expression because we can't do anything else. It's just any general x value. Now I'll put that square root of x plus 3 into the g function and see what happens. So the g function is x squared minus 3, but instead of x squared minus 3, we put this algebraic expression in, and we get this. And now we simplify this, and we hope we get back to x, because this is what we started with for any x value. The square root squared, again, will cancel out to x plus 3. And then minus 3. And that does equal x. So that's a yes. And we already showed the other one was a yes, the other composition. So therefore, we do know now that these two functions, f and g, are inverses of each other. Okay, so now let's just fill in these blanks, and then we can go move on. And hopefully I won't go this slow, and we can continue. So what about this one? They want us to check f of g of x. That's what we did over here. So instead of a particular x value, we're going to say for any x value. So we're going to put inside here, yeah, not a number for x, like the 4, and get 13, but for any general x value, the range value will be this x squared minus 3, just like we wrote here. So right here, we're going to type x squared minus 3. And yeah, so then what? When you put that into the function f, which is what we did right here, So put that now into function f, and there they wrote this plus 3 part. So now it's just like this part. So instead of writing the function f, which is just the x plus 3, we're putting this in instead. So now we're going to write this x squared minus 3 still, and you can put it in a parenthesis if you like. Which is the same thing we had right here. And then, oh, they're not asking us to show it here, but this does, we did it right here, this does subtract out. Negative 3 plus 3 is 0, and the square root of x squared is x, and then that's all they wanted us to do. Now this other one, which is this one. Put f of x into g. Again, not a numerical x value, but a general x value, any x value. That was this right here. So for any x value, when you put that into f, you just get this instead of a numerical answer. And that's what we wrote right here. Or right here. So we have the square root of x squared plus 3. I'm sorry. F of x was square root of x plus 3. Sorry. And that's what we have right here. Now when you plug that in, so now you put that in to function g, into function g. And so instead of this x squared minus 3, we're going to put this in instead. So that's why you still have the, just like right here, we have the minus 3. And now instead of x squared, this red x squared, we put the square root of x plus 3 in. And then we already showed over here how this cancels out and simplifies to x. Okay? Okay, so because these two compositions of each other get reduced back to the original x value, therefore, by the definition of inverse functions, these two functions, f and g, are inverses. Okay, so. So they liked our answers here, and we checked this graph, and they liked that as well. So that means everything is correct. So let's continue. Hope that made sense. And let's try a different one. Okay, now we're going to do it graphically, and then we'll do the testing this way, and we'll go many times faster. So first of all, the graph. How about we pick, doesn't matter which one we pick to start with. How about we pick this one? And let's put in a few points. The cube root function, and this is for g. So if we put a 0 in, the cube root of 0 is 0. 0 times 0 times 0 is 0. So the cube root of 0 is 0, so we get 0, 0. How about we put, how about we put 1? The cube root of 1 is 1. Because 1 times 1 times 1 is 1. Well, we're not going to always get these same answers. The cube root of 8 is 2. Because 2 times 2 times 2 is 8. Now, I didn't put a negative number over here on purpose because I noticed over here, let's take a look. So let's see if any of these points are on any of these graphs here. So 0, 0, neither one of these two graphs has, here's 0, 0, and it's not on either graph. So this cannot be the correct graph. There's 0, 0, and it's on both of them. Well, that makes sense because if these are inverses of each other, then we know from our discussion that if you have one function with ordered pairs or points, then if you invert these points on one function, 8, 2 is going to invert to 2, 8. And 1, 1, well, when you invert it, you just get 1, 1. And it doesn't feel like you inverted it, even though we did. And the same with 0, 0. So the two graphs are both going to have 0, 0 on it and 1, 1 on it. But here there'll be a distinction. Yeah, 8, 2 and 2, 8. So let's see if that's enough information for us to choose the correct graph. So we already said both graphs do not have, here's 0, 0, and it's not on G and it's not on F, so this one's out. Both of them have 0, 0, and both of them have 1, 1, so this is looking pretty good. Let's see about the point 8, 2. Well, they don't go that far. 8 over up 2, but that's reasonable to believe. And what about its inverse? 2, 8 would be the other one. 2, if I can go straight, it would help. It's kind of hard for me to do that. But if we go straight up, and I'm really not going very straight. This mouse is too sensitive. At least it's reasonable to believe here. So this is looking pretty good. And you can see here's the reflection line, y equals x. And if you pick any one of these and reflect, this little blue piece reflected over the reflection line gives you that black curve. And if you reflect this over the reflection line, it looks certainly reasonable to get this. So this is looking pretty good. How about any of the other ones? So here's the reflection line. 0, 0 is right here, and it's not on either graph. Even though these look like reflections, but they're just not the right ones. So this is out. And the same idea here. 0, 0 is right here. It's supposed to be on both graphs, and it's not. And the rest doesn't look very good either. So this has to be the right one. So that's that. And now we're going to show that they are inverses by doing this composition that we just did on the previous problem. But I'm going to go to my notebook because it's kind of tedious and it's not very neat, and I'm sure it's tedious for you as well. So I'm just going to write down the two equations, and then we'll show using the definition of inverses, or at least one of the definitions, and test if they are inverses or not. Okay, so I'm going to clear this and go to the notebook, and here we go. Okay, so we already matched the graph. We don't have to graph anything. We're just going to test if these are inverses. So we need to check the two compositions. So in no particular order, let's say, let me pick a colored pencil, that might help. if we have f of g of x, that's one thing to check. And another thing to check is g of f of x. And we're going to check, question mark, do we get x? Yeah. And the same thing here, question mark, do we get x? If we do, well, then they are inverses of each other. Okay, so here we go. Let's start with this one. So we have f of, so we're not picking a particular numerical value for x and putting into g like an 8 or something, but we're saying for any x value. So instead of putting a number like an 8 and putting an 8 here and the cube root of 8 is 2 and writing a 2 here, we are going to write the range value, not 2, but just as an algebraic expression. So what happens if you put an 8 here? Well, you get cube root of 8. But if you leave it as any x, if you leave it as a general representation, so x represents any numerical value in the domain of g of x, then the range value will not be a number because you can't simplify it. It'll just be this algebraic expression. So cube root of x. And now we put this cube root of x expression into the function f. Well, f is x cubed, but instead of x, we're putting the range value expression of g of x, which is this cube root of x. Simplify it. Well, if you put a cube root into a cubing power or powering of 3, they're inverses of each other, so they do compose out, and what's left? Whatever was inside there, which is the x. So that means for any x value we start and we put it into g of x, take that range value and put it into f, we do get back to the original x value. So that's a yes or check, and we're halfway there. Let's do the same thing with this one. For any x value, put it into f. If you put a numerical value into f of x, say you put say you put a 2 here, you'd get 2 cubed. 2 times 2 times 2 is 8. And then we could write an 8 right here and put 8, that range value 8, into function g. And then hopefully we would get back to the original x value, which is a 2. But we're doing this for, you have any or no? But we're doing this for any general x value. So instead of writing instead of putting a number into x and writing a number and getting a range numerical value and putting the numerical value here, we're going to put the range algebraic expression. So if you put any x into this equation, well, you're not going to get a number answer, you're just going to get x cubed still. So that's all we can do because it's general for any x value. Now plug that expression into g, which is right here, and we get the cube root of x, and we put x cubed into it. I'm sorry, got my colors mixed up here. So, and when you put x cubed in, when you put the powering function of power 3 into the root function root 3, because they're inverses, they compose out, and we get this x again. So it works out. But it gets kind of tedious to keep repeating all that, but I hope, otherwise, if I don't attempt to do so, then it's just, at first it seems just magical and we're just doing it, but we don't really know why. But from now on, I'm just going to do it, okay? Therefore, F and G are inverses of each other, or we can just say inverses. And we have that. If we go back to WebAssign, then they want us to fill these boxes in, and this was the first one, put g of x into f. Well, without repeating myself, this is the range expression for g of x, so we put that there. And I want to find, where is it here? Functions, maybe. Yeah. So the cube root of x, and that goes into f. So we put that right here. So here's the cube still. That cubed is that cubed, and now we just put this right here. And then when you do that again, you put the root 3 function into the cubing function, and because those are inverse functions of each other, they compose out to x, and that's a yes. And then the other way, put f of x into g. So put f of x into g, but not numerically, but the range expression for f is x cubed. So we put x cubed into g. And then they compose out as well. Okay. And we have those filled out. We have the correct graph, and we are good. So that's 19 and 20. We did the bottom two problems, 21 and 22 on part 1. There are a bunch of these that are now more practice, but I do want to show you one of these that's a line. Not that it's difficult, but I would like to show you. So 17. So x minus 5 and x plus 5. So for one is to match the graphs, and one is to prove they are inverses each other using this composition definition. So what about matching? So we have x minus 5 which is slanted line, x to the first power. So it's y equals x minus 5 slanted line. Let's put in a couple, 2 points is enough. How about 0? 0 minus 5 is negative 5. And then let's just pick another. How about whatever? 3. We could pick 5, but that's a negative 5. 3 minus 5 is negative 2. Well, then that must mean if these are really inverses of each other, then when we do this one, if we switch these around, and if we put -5, we better get a 0, because that's would be inverting these two. So let's see, if you put -5 right here, well, -5 plus 5 is 0. So that's a strong indication. Not absolute proof, but okay. Now let's see, since 3, -2 is on this graph, if we invert it and put -2, then we should get 3 right here. Well, if you put -2 up in here to function g, -2 plus 5 is 3. So yeah, so it's looking good. We could check a whole bunch of more points, but we're going to check it anyway right here for any x value. Okay, so knowing these two, f has to have these 2 points on it. G has to have these 2 points on it. And we know they're lines. And you know they're going to graph the reflection line, which is y equals x. So that should be enough information to help us figure out which of these 4 is correct. Well, first of all, y equals x we know goes through the origin and is increasing and has all, like x equals 1, y equals 1. The y and the x have to, if a point's on this line, which means it's a solution point to that equation, well then the x and the y values, if the point's on the line, then whatever x is, y better be the same thing, better be equal. So this looks believable. 1, 1, 2, 2, and so forth. Clearly, this is not y equals x because it doesn't go through the origin. So this one's already out without even looking at the 2 tables. So this one is out of there. Likewise, this y equals x, that's out of there. It's wrong. So it's either these 2. And they look kind of the same here. So which one? Well, again, let's use the points here. So 0, -5, and 3, -2 has to be on one of them. And not only one of them, but it has to be on F. So let's see. We know it's this one or this one. So 0, -5 is right here. And that says F. That's this F right here. So that looks good. And 3, -2 is supposed to be on the graph. 1, 2, 3. -2 looks very believable. And what about G are supposed to have these 2 points? So let's see. -5, 0. That's right here. And that's on the G graph, G. And -2, 3. -1, -2, up 3. Well, that looks pretty good also. So it's probably this one right here. I'm going to gamble and click it. What about this one? 0, -5. Oops, that's close. That's 0, -4. So they just tried to trick us a little bit here. So, and 1, 2, 3, negative. That doesn't look so good, but we already know it's wrong from right here. And we could have checked this one too. -5, 0 is right over here, and that's not on this. So this one's out. So it's this one. And now we're going to go to the notebook and prove that they are inverses. And notice they turn out with lines. They turn out to, in this case, because the slopes are both 1, they turn out to be parallel lines. It doesn't always happen like that. And let's go to the notebook. We have x minus 5, x plus 5. So number 2, or whatever number this was, we have f of x equals x plus 5 and g of x equals x minus 5. And I better double check. Nope. So much for my memory. X minus 5 is f and x plus 5 is g. Okay. So we're going to do the same thing as we did up here. So we're going to check the two compositions. F of g of x and will we get back to the original x value? Question mark. And the other one, just like up here, the other order of composition or composing the two functions would be and do we get x? So this one, I'm gonna go faster now, not repeat myself anymore. G of x is, here's the range expression for g of x. Put it right here. On this one, put the range expression for f of x instead of a range specific number. And that is x minus 5 and when we do that, so for this one, we write down f of x, which is x minus 5. And for this one, we write down g, which is x plus 5. But instead of g of x writing x plus 5 down, instead of the x, we put in f, which is x minus 5. So right here, we put the x minus 5. And on this one, instead of writing f of x down, which is x minus 5, we're putting the range value of g into the function f. So we're going to put an x plus 5 right here. Simplify, and we're supposed to get x if these are inverses of each other, and we don't make a mistake. Well, plus 5 minus 5 is 0, so we do get x. That's a yes. And the same thing here. So yes. So once again, they are inverses of each other. Okay? Hope that makes sense. So now we fill in these boxes. So here f of g, but what is the range expression for g of x? That's this part, x plus 5. Now actually put that into function f, which is right here, but instead of the x value, you're going to put the range expression of g. So this minus 5 is this minus 5, and then right here, we write instead of that x, we put this range expression x plus 5. That's either incredibly simple or it's easy to get confused. And these do simplify down to x. And likewise, put f into g. Here's f, the f range expression. Put it into g, which is this one right here. So there's that plus 5 is that plus 5, and instead of x, you put this range expression from f right there, x minus 5. They do simplify to x. And we're good. And we're correct, and we're correct. So I'll let you do 18. We did 17. Here's another linear one. Let me see what's left. Here, all you have to do is find which of these down here is the inverse graph. They don't ask you to do anything else. So you could just pick a point from some points here. Well, 0, 0 is on this original graph. Well, 0, 0 has to be on the other one. And all of them have 0, 0. So that's not enough. Then you have to keep going. Or you can just take this little shape right here, and there's more than one way you can do this. You can use the different ideas behind the graph. And I'm afraid I'm going to butcher this line. And -2, -2. And I'm almost, I don't use the word afraid very often, but it seems like I am. And it tells you how weak I am at using this mouse pen. Well, there's supposed to be the reflection line, y equals x. Then we're looking for the reflection of these pieces, and this is when I can really mess up here, and it looks something like that. And this part reflected will be something like that. And now we look for that one. And the only one that's close to my scribbling here is this one. So it better be that one. And we have it. Green check. Okay. Hope that's okay. So let's see. So depending on what's left here, I might do another line one. This is the same idea. Just graph the inverse function so you can figure out the inverse of this one graphically. These problems here are exactly what we were doing below, which was this part, showing that the compositions equal x in both order to show their inverses. And so that's what they're doing here. Same on number 12. And number 11, I think you guys can write that one in. Same thing here. So there's a lot of repetition here. Same thing, same thing, same thing, same thing, same thing. So let's just do one more and let me think about which one. Oh, so my apologies. So these, it's the same thing, all right, but you first have to get the inverse equation ourself. So I did show you that already in the discussion. So let's do one of these because there's one extra step. So let me just take a look here. So that's on number 8, number 7, up to number 3. Okay, so let's see here. How about number 8? Okay, so I'm going to write this down. And we have one of the functions, they only give us one of them, and it's x to the 5th over 4. So I'm going to go to the notebook now. And now we're going to figure out the inverse. So we can write here y, so y equals x to the 5th divided by 4. And we want to change f of x to y simply so that when we invert to get the inverse equation, so to find the inverse equation, we invert the x and the y. Really, if we just do that first step, so if we do that right here, everyone, we get x. Instead of y, we invert it and put an x. And instead of this x, we put a y. And those are the only two locations where there was an x and a y to begin with. So that already is the inverse. That's the inverse of this. If we could type this in, this is mathematically correct, but I don't think they're going to let us just leave it like this. So they're probably going to ask us to solve now for the new y. Even though, again, this is the inverse. Now we're just going to clean it up and solve for the new y. And that way, we can end up writing it like y equals, and then change this as the inverse of f. This over here was the name of this function. F of x was the name of this function, and which we changed this to y. So as soon as you invert it, the x and the y right here is now the name of, so y is acting as the f of inverse. So once we solve for y, we can just write f to the negative 1 of x. Okay, so how do we solve for this new y? Well, we use our algebraic skills to we have to get rid of the 5th root, and we have to get rid of the 5th power and the division of 4. So get rid of the division of 4 first, and to get rid of division of 4, we know we have to multiply both sides by 4. So we get 4x, 4 times x, 4x. 4 divided by 4 is 1. That's why multiplication of 4 will get rid of the division of 4. 1 times y to the 5th is y to the 5th. Now, to finish our task of solving for this new y, we want to get rid of the 5th power. To get rid of a power function, we have to do the inverse of a power function, which is a root function. And these compose out, and we get y equals the fifth root of 4x. So we can write y in the front, and y equals the fifth root of 4x. This is perfectly correct, just as this was perfectly correct. Or realizing now this is the name of the inverse equation, the inverse of this one, the inverse of x to the fifth over 4 is the fifth root of 4x. And if they name this one f of x, and we know this one is the inverse, then instead of writing y, we can say, oh, the fifth root of 4x is the inverse of this, or you can say the inverse of f, which is this notation. So that's what we're going to put in WebAssign right here. F inverse is the fifth root of 4x. It's kind of dangerous to say this, but we have the original function has power of 5 and division of 4, and the inverse of power of 5 is root 5, and the inverse of division of 4 is multiplication of 4. This division of 4 was outside of the powering function, and when you invert it, it becomes multiplication inside. That's a dangerous way to think about it, but it does work in this case. Now we have to check this. So going back, which is the composition, and if we go back now, so now we check. So by the way, it kind of seems redundant because we already shown that this is the inverse of this. Now they're asking us to confirm that this and this are inverses by using the composition definition or idea. So, okay. So we're going to check 1, f of g of x does that equal x? And then the other one, does g of equal x? So on this one, we take the range expression for g of x, which is not function f, the other one, which is this one. And we're going to plug that into function f. Well, here's function f. So let's write function f down. I'm very lightly writing the x and with my pencil over 4. That is, this is f. All right, there it is. But all I've done is written f of x because I just left, if you put an x value into any x number into this function, you would just put it right here. But so if you say in general any x, well then you would just get this stuff. But we're not supposed to put any x. We're supposed to put the any x is going into g, which is this one, and we're not putting a specific number in here. If we did put a specific number in here, if they told us to, then we would get the range value right here. Let's say you put a whatever, a 2, 4 times 2 is 8, and you put the fifth root of 8, and that would be the range numerical value, and then we would put that into F. But they're asking us to show it in general. So in general, for any x that goes into, this is our g right here. For any x we put into function g, we get the fifth root of 4x is our range expression. So I hope that makes sense. So this is g of x. So that's what we put right here. So that's the fifth root of the 4x. And we hope this reduces down to x. On this one over here, f of x is the range expression for f of x is this. We're going to put this range expression into the other function right there. So this becomes let's write down what g is. G is the fifth root of 4x. That's what g of x is. But we're not just putting, finding g of x, we're finding g of f of x. So what is the range value for f of x? It's this one. And so we're going to put this one right here. X to the fifth over 4. Now we simplify both of them. This one, for example, the 4 divided by 4 divides out. We're left with this fifth root still of x to the fifth. They compose out to x. So yes. This one, the multiplied 4 is inside this root. So, and this division of 4 is not inside. So you can't divide, I mean, if we divide them first, you won't maybe not even think you're doing anything wrong. But you really have to get rid, because the multiplication of 4 is inside this root. So you can't get rid of the multiplication of 4 first, but you can get rid of all of this 4x is inside the fifth root, and all of this fifth root is to the inside the power of 5. So these compose out first. And what's left now? 4x over 4, which equals x. So that's another yes. So because these two compositions do both get back to the original any x value, then we know they are inverses. F and G are inverses. Go back to WebAssign. And this was number, I don't know. This was number 8. So we already had found the inverse before, a few minutes ago. Now we're doing this part. So F inverse, which is like our F of G. So what goes right here? The range value of whatever is written here, which is the range value expression for F inverse of X, which is this one right here. So this part right here, the range value for that, the range value expression for that is this part. And so we put that right here. And now when you put this into function f, here is function f, but instead of right there, you're going to put this range expression, and you're going to put it right there. So the division of 4, see this red division of 4, it's still here. This powering of 5 is still right here. What goes inside this powering of 5? Well, this part. So and then we showed how the fifth root composes out with the powering of 5, and then all you'd have left is 4x divided by 4. The 4's would divide out to 1, and you would be left with 1x or x, and that was a check. That's what we did on our paper. And now this one. F inverse of f, that's the other order of the composition of the two functions. So now we put the range value of f of x inside this function. What is the range value expression for f of x? It's this part. And we're going to put this range expression in, which is the range expression. This means the range expression for f, I'm sorry, down here, for f of x. So what is the range expression for f of x? It's this. So we're going to put, instead of f of x, we're going to put its range expression. So right here, we copy it. And I don't know what happened there. It doesn't, I guess it didn't want me to copy that. So we have to type x to the 5th divided by 4. And now when you put this range expression, excuse me, into f inverse, which is this one right here. And so here is f inverse. Put this expression into f inverse wherever, and here's f inverse. And so instead of this x right here, you're still going to have the fifth root. You're still going to have the multiplied 4, which is right here, fifth root, the multiplied 4. But instead of that x right there, you're going to put this expression right there instead. So right here, we have, maybe it'll copy this time. I'll find out. So let's see. It did. And now simplify. This 4 and this x to the 5th divided by 4, they're all inside this 5th power. So, and this 4 is not inside the powering, but these can divide out. First, 4 divided by 4 is 1. 1x to the 5th is just x to the 5th. The 5th root of x to the 5th composes out to just x, like we did on our paper, and that should do it. And there we go. And everything is correct. So there's two more like that. Well, let's see, maybe more than that. So these up here, you just have to first find the inverse. And then you're going to do this part like we've been doing. How about we do one more of just the first little piece here? And how about we do this one? So I'm just going to do it right here. And so take this, change this to y, we have y equals x squared minus 5. Switch, invert the variables. So instead of y, it gets inverted to x. Instead of this x, it gets inverted to y squared. This already is the inverse equation, but not taking into account any domain issues, because remember right here, there is a domain issue. X has to be greater or equal to 0. So that means on this, the range will have to be greater or equal to 0. So because of this domain of the original one is greater or equal to 0, and then when you invert, instead of x being greater or equal to 0 on the original function, y will have to be greater or equal to 0 on the inverse function. So when we continue now, that's one of the reasons it's nice to solve for y, because some cases you will have to eliminate the positive or negative piece based on this restriction. And that only happens when this is an even power, which means this would have had to have been even power. Solve now for the new y. Solve for the new y. And let's just do that quickly. To get rid of a subtraction of 5, we add 5. So we have x plus 5 equals y squared. This adds up to 0. And now to get rid of a square, squaring, to get rid of a powering function of power 2, we need to do the inverse of power 2, which is root 2. Root 2, you don't have to write the 2 when it's a root 2, it's square root. And these compose out, it's really absolute value. Well, we'll skip that step and you get y equals plus or minus the square root of x plus 5. So, but remember, y has to be greater or equal to 0. So if you take a square root function, which is always a positive value, times this negative in front, that would give you a negative value, and y cannot be negative because y has to be greater or equal to 0. So that forces this negative piece to be eliminated, and so we get the inverse equation is just this, the square root of x plus 5. And then of course, because that is the inverse, then we can write x plus 5 is the, instead of writing the y, we can just now put f of negative 1. Because this is the original function, they named it f. So after you invert the letters, solve for the new y, and now we have, then you could leave it like this. It's just more specific to say, what is this new function right here, square root of x plus 5? Well, it's the inverse of this initial one. So if they told us the name of this initial function is f, then the name of this new second function, which we know is the inverse of f, we might as well be more specific and write f to the -1 of x, which means f inverse. So that's what goes right here. And we write x plus 5. And then you have to do this, the two compositions. But I think we've practiced that quite a bit already. So I'm going to leave that for you guys. And anyway, we did one like that down here somewhere. At least I think. I could be getting mixed up, but maybe it, oh yeah, right here. Very similar, number 20. Okay, so, okay everyone. So I hope this gives everyone a chance to better understand the concept. And we've done some of your homework problems together as well. And so you have these remaining. And so with that, I wish you all the best. And you can always, when you watch this, honestly, I just discovered that you can play on YouTube, for example, you can play the videos at a faster speed. I never knew that until a couple hours ago. And so if I take too long, and don't say I do, okay? Because I'm trying to help you. But you can always speed up the speed at which I'm talking, and so do what works for you, okay? Okay, everyone, so on Thursday will be our last lecture session, and it will, unless something goes wrong like today, it will be at 11:30 on Thursday. I have office hour tomorrow at 10:50 to 11:20 if you need any specific help, and the same thing on Friday, okay? And I'll be emailing you to talk to you about our last exam and our final exam coming up. Okay, so keep working hard, everyone, and goodbye for now, okay? Thank you. Take care.